I want to turn now to dealing with the problem that I mentioned previously, that the plane wave solution to the Schrödinger equation for a free particle is not normalizable and therefore cannot represent what we think of as a particle in any meaningful sense. It turns out, though, that we can get something that's particle-like by adding up multiple plane waves. So it so happens that the Schrödinger equation is a linear partial differential equation. I'm not going to go through the proof of this, but you can show that psi of x t equals a e to the I k1x minus omega 1t plus b, I don't just call this a1, plus a2 e to the I k2x minus omega 2t is also a solution to the free particle Schrödinger equation. In other words, we can add up different plane waves. Now, these are all plane waves going to the right. We can also add plane waves that are going to the left. Also, right, psi xt equals b e to the I. This time I'm going to write it as minus kx minus omega t is a solution. So I think you can convince yourself that with both of the terms in the exponential having the same sign, sign sign, this is a left-going plane wave as a solution. So linearity means we can build up solutions to the Schrödinger equation by adding up multiple plane waves. The idea of building up solutions by adding up other things, that's actually going to be a really deep idea we see in a couple other contexts. When we get to chapter 4, and it's chapter 3, I mean, and it's definitely an idea you'll explore in more depth in Physics 421. Those of you who have had some linear algebra might start to see some hints of things you might have seen in that class. But anyway, so it turns out that the most general solution of the Schrödinger equation for a free particle is to not just add up discrete plane waves, but to add them up in a continuous sense, aka via an integral. So the most general sum, so a continuous sum of infinitely many plane waves. So maybe I'll just write out the discrete sum first, actually, just so that you can see where it comes from. The discrete sum would look something like psi of x. T would be some summation. Right, that is a sum over, I'll use k as my index. So it'll be something like sum over k, a sub k, so I'll use that like, like a1 and a2 here, a sub k e to the I kx minus omega t. Well, the continuous version of this is turning the sum, so this is adding up a whole bunch of plane waves, where the plane waves have different amplitudes, a sub k. The continuous version of this is an integral. Psi of xt equals an integral from minus infinity to infinity of a of k. We now let the amplitudes, rather than being discrete, be a continuous function that depends on k e to the I kx minus omega, and I'll write omega sub k following Townsend because there'll be a different frequency for each k here, omega k here, and I should have probably put a sub k up there as well. And we're going to integrate with respect to k. Hopefully you can see the parallel here, right, turning the discrete sum into a continuous integral. And this is our most general solution to the Schrodinger equation for a free particle. Now, I don't know about you, but it's really hard for me to have sort of intuition about this expression here. This looks kind of nasty. It's an integral over k, which we probably aren't used to thinking about integrating over wave numbers, and this thing here is complex to boot. So at this point, what we're going to do is to look at some visualizations and simulations on my computer to help us get a more concrete understanding of what happens when we add up different plane waves. And it turns out we can build up something called a wave packet. Okay, so this is the Fourier FET that I'd like you to look at. In the slides, I also gave you a link to another animation that's from NYU. I think this one I like better because you can interact with it more completely than the NYU one, but if you can't get this one to work for whatever reason, you can take a look at that as well. Anyway, what you can take away from this is the following. So we're on this discrete panel here. What this is doing is this lets you add up different sine and or cosine functions. So just let's walk through what we have right here. So right now we have A1 and it's got an amplitude of 1 and there's nothing else in there. So this is a sine wave with some particular wavelength. Now if I turn on this A2, right, I get something that's the orange A2 has got half the wavelength, or in other words, double the spatial frequency k, double the wave number k of the first wave. Similarly, A3 has got a third the wavelength, or 3 times the wave number of this red A1 wave, wave number 1, and similarly. Now what you can see is you see the individual waves plotted in this middle panel here, and then their sum is plotted down here. Now, depending on how I slide this, right, I can change the amount of this this sign relative to the red one. Okay, so the physical things to take away from this. I'd first like you to recall what you probably learned in Physics 217 about beats. So you might remember if I take, say, we put in A8 here, if I combine two sines or cosines with slightly different wavelengths, so let me mix in A8 and A10, so they're fairly close, and I'll click this auto scale here. What you see is we get a beat pattern. You can see the envelope up here, it gets small and it gets big again. I can even zoom out a little bit maybe. Yeah, there we go. And you can see more of this beat pattern emerge. And maybe you probably talked about this in 217, with like musical instruments, where you can literally hear the sound going or something like that. Things to note about the beat frequency, right? The beating and the frequency of the envelope here, or in this case, the wavelength of the envelope, since we're talking about position dependence and not time dependence here, right? If I make the wave number difference between the waves smaller, notice how the beat pattern gets stretched out compared to what it was before. And if I make the wave number difference larger, so if I combine, say, A8 and A11, notice that I now get a beat pattern that has a shorter wavelength. So this is an important thing for us to keep in mind, sort of this idea of beating. And what we're going to do is to try to generalize that. So notice that when we had this beat here, so if I bring this back up, notice how we still have a completely repeating periodic pattern. This still doesn't help us solve the problem of getting a wave function that can be normalized and that could represent a particle. Well, it turns out we can do that or get something closer to that if we start combining more than two different signs. So I'm going to set wave packet here. And you can see now that what we've done is now we've added up a whole bunch of different sine functions. And lo and behold, we have something here that now starts to look a little more localized. Now that's a little deceiving because if we zoom out, we can see that this is still periodic. We still get this sort of bloop, bloop repeating periodically. So we haven't yet solved the problem, but maybe we can see how we can get closer by adding up more than two sine functions of different wavelengths. Okay. So, how do we get something that's really localized and not periodic? It turns out that the answer is to do a continuous sum, like I mentioned on the board. So let me go now to this discrete to continuous tab here. So once again, right now, we are adding up a bunch of different sine functions. So that's what's denoted by this bar graph here. Right now, we're still adding up discrete wave numbers. And what we're plotting here is the spacing in wave numbers between adjacent sine functions. So once again, this is the same case essentially as we saw on the last panel. We still have something that looks periodic. Now, what if we increase the spacing between the sines we're adding up? So if I drag this slider up to 2 pi, now we kind of see, well, things have gotten maybe worse from the standpoint of getting something that's not periodic. We've got sort of a shorter periodicity than we had before. But things get interesting if we start dragging this slider over to the left here. So if we now decrease the spacing between the sines, notice this maybe is getting more and more localized. I have to zoom out quite a bit now to see the fact that this is still periodic. If I slide this over to pi over 4, now the signs I'm adding are getting closer and closer spaced together in spatial frequency, or in wave number. Sorry, I keep saying spatial frequency because that's optics language that I'm used to. As we get closer and closer spacing in wave number, notice how we're getting more and more of an isolated blip. And if I drag this all the way over here, so that we're doing not a discrete sum, but a continuous sum, like the integral I talked about, lo and behold, well, we have an isolated blip of waves. This is what we call a wave packet. So to reiterate, a wave that has a well-defined wavelength or wave number, right? And that's what we showed was a state, was a wave function for a free particle with a definite momentum. That can't really represent a localized particle because the wave function is sort of everywhere. But if we add up a whole bunch, a continuous sum of those sine waves, we can in fact get something that is localized. And hopefully just from looking at this, if this were to represent, say, the real part of a wave function, hopefully you're convinced that this looks like it's something we could normalize. So there's one more thing that I want to point out here, which is the following. So we've got two more sliders I want to pay attention to. So we have the width of the wave packet, so that is how wide the range of wave numbers we're including in the sum is. And we can also have the width of the wave packet here, right? And so as we plot the sum versus position. Notice what happens if, so we're at 3 pi now, if I make the wave packet narrower in the range of wave numbers I include. So if I drag this to 2 pi, narrower. If I drag it to pi, this is getting wider and wider. If I drag this all the way to 1, now we have a much wider wave packet. Similarly, if I increase the spread in the wavelengths I add up, or wave numbers I add up, right? Notice that a wider range of wave numbers gives me a narrower wave packet. This really is the heart of the Heisenberg uncertainty principle. I'm going to write it down on the board after I exit this. I'm not going to try to give a rigorous proof of the Heisenberg uncertainty principle now. You can do it using more sophisticated techniques in 421, or maybe we'll have time at the end of the course. But I think this, to me, is sort of the playing around with this, just like we're doing now, is the best way to get an intuitive feel for the Heisenberg uncertainty principle. Remember that in quantum physics, wave number or wavelength is associated with momentum. So a pretty narrow spread in wave number is associated with a narrow uncertainty, a small uncertainty in momentum. Our exploration of wave packets has hopefully let us see something really important. That if I have just a single wavelength, right, then I get something, I get a plane wave that has infinite spatial extent. As I increase the range of wavelengths I sum up, I get a wave packet that's more and more narrow, or more and more tightly localized. Now, this is not a proof, and frankly the best way to prove it is using some more sophisticated techniques. Townsend talks about it in chapter 5. We may or may not get there, but I think you'll do a rigorous proof of the uncertainty principle if you take physics 421. But it should suggest a certain amount of plausibility for the following statement which we call the Heisenberg uncertainty principle. And that says that the uncertainty in x times by uncertainty in momentum, and I'll label that. I've been sloppy notationally. I'll label. We're working in 1D, so I'll label this p sub x here. Is going to be greater than or equal to h bar over 2. So we haven't given a proof of this, but hopefully it's plausible based on what we've seen so far. So at this point, what I'd like to do is I'd like to close today with with another clicker question. When we come back, on Monday, we'll have some more things to think about. We sort of maybe have some intuition for what delta px means in terms of a spread in momentum or a spread in wavelengths. But we have yet to understand how to rigorously calculate delta px from the wave function the way we know how to calculate delta x. So we'll have to talk about that next time. But we've today introduced some ideas, and let's do the clicker question and then I'll sum up. So having thought about the clicker question, right? So if we think about the Heisenberg uncertainty principle, right? If we want to know which particle can have its velocity known most precisely, that means we want delta px to be as small as possible. Now the fact that there's sort of a lower limit to the total uncertainty, or the product of the uncertainties, right, delta x, delta px equals h bar over 2, right, that suggests that if I want a smaller delta px, I'm going to need to have a bigger delta x. We do have some intuition for what delta x means. It's the width, essentially, of my wave function. And if we look, it's at the choices, right? It's C. That's the one that's the most spread out. So C is most spread out. So it has the largest delta x, sorry. And therefore, it could have the smallest uncertainty in momentum, could have delta px, or in other words, it's C that could have its velocity known most precisely. Okay, so now I'll sum up. So today we've looked at the Schrödinger equation, we've looked at solutions to the Schrödinger equation for a free particle, and we saw that those are plane waves. We've looked at how we can build up something that is localized and maybe particle-like, a wave packet, by adding up lots of plane waves. And from playing around with that kind of superposition, we've introduced the idea of the Heisenberg uncertainty principle. And we'll continue discussing this and momentum in quantum mechanics next time. See you then.